So I got into optics quite late in 2012. First I studied chemistry in Leiden, then I did a PhD in nanoelectronics in Delft, and then only in 2012 when I moved for a first postdoc to MIT, I started working with optics. And yeah, this was a big adventure because I joined the group of William Tisdale at the Department of Chemical Engineering there. The group didn't exist yet, so I was the first to join the group, and we basically in the first year with a very young team of students, we built the entire lab. Yeah, and so most importantly we developed this technique that allows you to make movies of how energy carriers move through the material. And these movies, they're just like a few nanoseconds in duration, but they give you an incredible resolution in both time and space. It's a super resolution technique which allows you to basically really see the flow of carriers through this material. We now refer to this technique as transient microscopy, and it's been around now for about 10 years. Many groups in the world have implemented this. I myself took a little break for 3 years as a postdoc at ETH Zurich, and then in 2017 I moved here to the Autónoma in Madrid to start implementing this technique again, also here with various microscopies techniques. So in this new project, it's an ERC Consolidator project, EnVision. We're going to really try to zoom in as much as we can on this transport of the carriers through complex semiconductors. Semiconductors which have a lot of variation in their energy landscape. And try to correlate the energy transport with these local energy landscapes. But on top of that, take it one step further and try to engineer these energy landscapes in such a way that you can get optimal energy transport, engineer traps, engineer energy gradients, try to influence the local composition of the material in such a way that carriers go downhill and the transport is faster and farther than what it would be in a flat energy landscape. So this is kind of what we refer to as a functional disorder. So of course, this is not an easy task. It's a challenging project. We're going to have to, image the carrier diffusion at the same time as that we are mapping energy landscapes. You get a lot of information, and in all these different dimensions of your data set, you need to look for these signatures of this enhanced carrier transport that then allow us to go back to the material and design. Right? So it's a combination of spectroscopy, microscopy, but also in a very strong part. Materials design, and there's a lot of questions there. That's simply where we're going to need the time and the resources to be able to give answers. So for me, the main benefit of a project of this size is at the end that it allows you to take risks. Basically because you don't need to worry about resources and funding for the next few years. You really have a critical mass of these resources in terms of manpower, in terms of equipment, to explore things that if they work, it will be a big step forward. And this is of course a little bit the idea at the end of the ERC program, which is the high risk, high gain idea. In reality, it also feels a little bit like that. It's really an opportunity to focus on more complex problems. Yeah, and of course, even in the longer run, all these different smaller ideas that we're going to be developing between this project, each PhD student, each PhD project is in a way going to give a new line of research, and hopefully this will, set out new trajectories beyond the duration of this project. So it's also the creativity of the team that comes into play a lot, and the larger your team, at the end, the more creativity that is there.